Hello and welcome to this presentation on the colour chemistry of vanadium. First of all, we need to have a little look into the background of vanadium. So take our periodic table, and it's here in the D block as a transition metal element in the first row. It has 5 electrons, 2 from the S and 3 from the D, and due to this it has some useful properties such as for making alloys in these chromium, molybdenum, vanadium knives, and in catalysis such as the contact process which makes sulfuric acid. The practical investigations of vanadium color complexes will consist of some redox reactions, one where vanadium is reduced and one where vanadium is oxidized, some ligand exchange, and importantly spectroscopy will be used throughout. UV-vis spectroscopy is a very useful analytical tool as peak absorbance wavelengths can be identified, and a different colored species will have its own peak absorbance wavelength. The peak absorbance wavelengths will be found within the visible light spectrum, and this can be done using a vernier UV-vis spectrometer where the samples that are measured are loaded into a 1 centimeter cuvette. The first practical aspect to consider here is the reduction of vanadium, where ammonium metavanadate and sodium hydroxide are used to provide the vanadium source, sulfuric acid for solution acidification, zinc as the reducing agent, and I will briefly cover how hydrochloric acid and mercury dichloride can be used with zinc as the reducing agent. First of all, the reducing agent needs to be prepared, where some zinc powder, harmful to aquatic life, will be taken. Mercury dichloride, which is toxic, has long-term health effects, corrosive, and also toxic to aquatic life, is made up to 0.1 molar in a hydrochloric acid solution, which is itself corrosive and an irritant. And this is just done with some swirling and then washing with water. This is to remove the mercury. However, this entire process uses mercury, which is not good for you or fish. And then you have zinc powder or mesh. This can also be used by itself as a reducing agent. As discussed before, it's hazardous to aquatic life, and this is a lot cheaper than using mercury chloride, where mercury chloride is about £170 for half a kilo, whereas zinc 34 quid per kilo. Just makes sense. For the reduction of vanadium, a vanadium solution is required. This can be done with 2 grams of ammonium metavanadate being dissolved in some sodium hydroxide. The ammonium metavanadate is toxic, has long-term health effects, and harmful to aquatic life. Sodium hydroxide, corrosive and harmful. This solution will need to be acidified for the reduction to occur, and that is done with some corrosive sulfuric acid at 3 molar concentration. And this solution that will have been acidified then needs to be poured into the larger volume of water as to not cause any issues with adding water to acid. This way it stops that. Little thing about pricing, the ammonium metavanadate could be considered pricey at £130 for 500 grams. However, the vanadium from this reduction can be used for other reactions, as we'll see. Sodium hydroxide and the sulfuric acid, they're a common purchase. They're not really the most expensive consideration out there. In order to do the reduction of vanadium, the vanadium solution should be put into a suitable container such as a conical flask. The peak absorbance wavelength of the yellow solutions should then be taken, and then the zinc powder should be added. Once the zinc powder is added, take a sample of the solution, now that the reduction has begun, and put that into a cuvette and into its own UV-vis spectrometer so that the peak absorbance wavelength can be monitored throughout the entire reduction. The vanadium species VO2+ is in the +5 oxidation state, and this will be reduced to the 4+, the zinc being oxidized from 0 to 2+. The vanadium will then be as a species vanadium oxide 2+. Now, this reaction will have an intermediate colour of green, because yellow and blue. Once the solution is green, the peak absorbance wavelength should be taken and should also be recorded from the cuvette that is just running the reaction by itself. The second reduction will take the vanadium from 4+ to 3+, and the solution will be an emerald green. The peak absorbance wavelength of this green should be taken and compared to the earlier green's peak absorbance wavelength. The third reduction will see the vanadium reduced from 3+ to 2+ to provide a violet pink solution. This vanadium 2+ solution will be very useful for other vanadium colour reactions. The oxidation of vanadium can be demonstrated with a series of potassium permanganate titrations. First of all, a vanadium 2+ aliquot was required. Whilst this could be done with using some vanadium dichloride, which is corrosive and harmful, it's not the best price-wise, as it's roughly £50 per gram, when vanadium 2+ that is be made from the previous reduction could be used, and the hazards should be assumed to be as before: corrosiveness from acidification, toxic long-term health effects, and harmful to aquatic life if not disposed of in the correct way. Some sulfuric acid is required in order to allow for this oxidation, so some further acidification. And as said before, this is corrosive, and some 0.1 mole of potassium permanganate for the titration. Now, potassium permanganate is oxidizing, has some long-term health effects, is corrosive, an irritant, and also harmful to aquatic life. The oxidizing factor, less of an issue, as it will be used in lower concentrations. The rest should be considered as they otherwise have been with the acid or the vanadium solution. With the oxidation of vanadium, there needs to be some consideration to the molar ratios of zinc and ammonium metavanadate that were previously used in the reduction. So, if this permanganate is titrated into the solution of vanadium 2+, there will be the oxidation of vanadium 3+. However, any presence of zinc will begin to reduce this back down. So, knowing that the reductions have a stoichiometry of 2 moles of zinc to 1 mole of vanadium, it can then be calculated how many moles of zinc you should have left in the solution. From this, you could work out how many moles of zinc are actually in the 10 ml portion, 10 ml aliquot that you're using. And this would mean that the volume of potassium permanganate solution being titrated will be larger in terms of moles than the actual moles of vanadium. And this could be a consideration to work out, as the stoichiometry is 5:1 of vanadium to manganese, or vanadium to permanganate. This means you should be able to work out how many moles of vanadium would have been in the solution that was reduced, and therefore you should be able to work out the concentration. Then that will be the concentration of this 10 ml solution. And from this, you should be able to work out how much potassium manganate, in terms of moles, should actually be used, and you can translate that to volume. Then you can work out how much excess volume you've needed to compensate for the excess zinc in the solution. Then, once the titration is complete, take down the measurement, the volume that was used, and once this green solution is reached. Now, whilst permanganate is a dark purple, manganese 2 plus is supposed to be a pale pink. However, the colour shouldn't be too intense. It shouldn't affect this green colour. However, it's always worth checking it through UV vis to see if there is any contribution to the colour species from the manganese 2 plus. However, you do expect the manganese 3 plus absorption that was previously measured. And then move on to the next oxidation, where the vanadium 3 plus green solution has potassium permanganate titrated against it. Now here, the stoichiometry changes slightly as a vanadium oxide species needs to form. Some of the oxygen from the permanganate will contribute to this. Slightly changes the amount of acid that's needed, and this also changes the stoichiometry of vanadium to permanganate from 5 to 1 to 5 to 2. This should mean that more permanganate should be required than in the previous oxidation. And then this will reach the blue solution, and then final titration of permanganate into the vanadium oxide blue solution. Again, has the same stoichiometry as previous, as is going from vanadium oxide to the vanadium dioxide, which will be the yellow solution. When any new colour is observed, let's say clear, stable colour such as the blue or the yellow, again measure the peak absorbance wavelength. There should be a green transition colour, as it's just the inverse of the first step in the reduction. Now I'll cover a couple of ligand exchange reactions. First of all, take some of the vanadium solution from the previous reduction, as there should be a nice amount of that, and then again assume the same hazards: corrosive, toxic, long-term health effects, and harmful to aquatic life. And this is the violet solution. This is the hexahydrate vanadium 2 plus, and then there'll be the need to take some BIPI, and it'll be a methanol. BIPI is toxic, methanol, flammable, toxic, and long-term health effects. As potassium iodide, this will help form the complexes. Once all these reagents have been added, give the conical flask a little swirl. This should produce a nice dark green solution. Take the peak absorbance wavelength of this solution, and this would be the species that should be giving the dark green solution, the tris-BIPI. And the overall reaction where the ligand exchange happens, you have the 6 waters and the 3 BIPI, as it's a bidentate ligand as opposed to monodentate. Then the 3 BIPI in the complex, and then the waters exchange. Second ligand exchange to be looked at, again, take some vanadium from earlier on, these familiar hazard symbols, some hydrogen peroxide in a fairly low concentration, however still considered corrosive, some sulfuric acid, corrosive, and then some of this PAR dye. Take this PAR dye in a rather low concentration, and it is expensive at roughly £280 per 5 grams. So, and also not a lot of it's needed. Again, here we have the hexahydrate vanadium 2 plus. First, the peroxide needs to be added. This will form a vanadium peroxide complex. However, it may pale the solution, and if you want to, you can take the peak absorbance wavelength. Solution needs to be further acidified, and then the PAR dye is added, and this should result in a nice red color solution. And then take the peak absorbance wavelength of this. This is the real color that we're interested in this reaction. Overall, the reduction of vanadium with zinc only is better than with mercury, as mercury is not great, expensive and toxic. Oxidation of vanadium, a nice series of titrations, gives you the same colors but in a reverse order. And then the ligand exchanges, you've got the PAR dye and the BIPI. we've seen some greens with the reduction, so perhaps the par is nicer as it is red. So thank you for listening.